here we go, ladies and gentlemen. Our first day here in pre-cal, we are looking at exponent rules, which, again, I hope this is review, but it may not be for some of you. Hopefully it is, but it's just might be a little harder level. So use and apply properties of exponents. So exponents are really, really important, and just so that we recall a few things. What is like 7 squared? What does it mean? Not what's the answer. 7 times 7, thank you. 7 times 7, which of course is 49. So with numbers, we can clean them up. We can actually do the operation. And something like x to the third power, what would that mean? X times x times x. Very good. So we know this. I just want to make sure. And so, a monomial, what's mono? 1, yeah, is a constant variable or product of numbers and variables. It's a single term, okay? A single term. And so for this, we have a few examples here. Something like -7 would be considered a monomial, or maybe something like 12xy, that might be a monomial, or something like -24 x squared y cubed. Okay, all of these are examples of monomials, one single term, connected by multiplication. All things multiplied together. So we are looking at simplifying monomial expressions here today. So that one is sort of interesting looking. Okay. So we have first, I like to lead by example as opposed to giving you a rule first. So maybe I have some things I want to clean up. Let's say I have a to the second times b, I'm sorry, not b, a to the third. And I want to clean it up because a to the second times a to the third, I think I can condense it. I can make it better. A to the fifth. Good. No, but why? Why? Sasha.
Because one side there is 2b and the other side 2a and the other side 3a. So
very good. Yeah. So I like to go back to the meaning because it's kind of weird to say you add them, but it's multiplication. Why? Right? So it's just kind of weird. So when I'm teaching, I'm always going to go back to the meaning. And of course, when we expand it, we can see, well, how many a's are there? A to the fifth power. Yeah. So, and of course, we like shortcuts because having to write everything out, well, that would just be lame. So if we can find a shortcut, then we can use it. And as you said, if they have the same base, we can add the exponents. So if we have a to the b times a to the c power, I like to throw in lots of different letters for you here. If they have the same base, the base stays the same, whatever it happens to be, and then all we have to do is add the exponents together. So a to the b plus c. And that's important that the base stays the same. All right. We have the power rule next. And again, I like to look at examples. Maybe I have like y squared to the fourth power. This is what I like to call a power raised to a power. So it's a power, but then it's also got another power on it. What do you get there? Y to the eighth, good. And again, we could write it out if we wanted to. We could say it's y squared being written out 4 times, being repeated 4 times. And of course, now this is a product, and we can apply our same product rule. 2 plus 2 plus 2 plus 2 is y to the eighth. Again, we don't have to write everything out, but this is where it comes from, and I think it's important to remember, okay? So when you have a power raised to a power, what do we have to do with those exponents? Just multiplying, yeah. So if I have x to the a raised to the b power, the base of x stays the same, and all I have to do is multiply a times b. Multiply your powers. All right. Quotient rule. Quotient is what? Answer to a division problem. Good, good, good. All right, so if I have something like x to the 7th divided by x to the 4th, x to the 7th divided by x to the 4th, what do you get? X to the 3rd is correct. Very good. So again, if I wanted to think about, but why? Why do we get that? And I really like thinking about it this way, but if you don't want to write this all out, you don't have to, but I am just going to show it. Again, I could expand this 1, 2, 3, 4, 5, 6, 7 x's. Really annoying, isn't it? 1, 2, 3, 4 x's expanded out. Again, why does it become x to the 3rd? Because they reduce. They're really reducing. You can imagine if it was like 3 over 3. Well, what is 3 over 3? 1. It reduces to 1. So all of these, x on top, x on bottom, they really reduce themselves away. And we're left with x to the 3rd. Oh, guys, I didn't scratch one off there. X to the 3rd. So the quotient rule, if I have x to the a divided by x to the b power, b exponent, the base stays the same. The base is x. And what do we do to the powers? Subtract them. And we subtract them top minus bottom. Top minus bottom. And it's important that you understand that these rules all apply when we have positive and negative exponents. They all still work. Okay? So very good. What does it mean when we say something like y to the negative 2? I think you might. Yeah. So a negative exponent, I like to think about it as an unhappy one. He's an unhappy exponent. Right now, this thing is upstairs, if you will. It's upstairs in a numerator, okay? Its exponent is unhappy. And so it's saying, hey, this whole thing is unhappy where it is. That whole thing wants to move and go downstairs. It wants to go to the denominator, okay? This becomes 1 over y squared. Negative exponents mean they're in the wrong place, okay? So if they were in the bottom, if they were in a denominator and it was a negative exponent, where does it want to go? It wants to go to the top, okay? And that's how I think about it. They can trade positions, okay? It is a reciprocal. Yes, that is the word. So if we have x to a negative exponent, x to the negative a, that is really the same as 1 over x to the a. But it really just trades positions. If it was in the denominator, it'd want to move to the top. Okay, and when it moves, it becomes positive. It becomes happy. Okay. The zero exponent rule. What is 273 to a power of 0? 1. Always, always, always. Any number to a power of 0 is 1. What is, trick question, x squared y to the 0? What is x squared y to the 0? X squared. Y to the 0 is 1. So this is just 1, and that leaves x squared times 1, or just x squared. All right? All right. Anything to a power of 0 equals 1. That is the rule. Anything to the power of 0 equals 1. And just in case you're a little curious, this is kind of a little side note here. 0 to a power of 0. Weird, huh? It is undefined. Crazy, okay? So this base cannot be 0. It makes no sense if you think about, would you ever have 0 squared? 0 to the third? Why would we ever do that? Okay? So it really doesn't make much sense. Okay. We want to clean up a bunch of these, figure out what we're doing here. Here we have a product of two things. This is really interesting. Boy, I don't know 6 to the 4th. We might need some calculators. Will you guys... Oh, lots of you grabbed them already? Sweet. I did not. All right. So feel free to grab a calculator. The one that matches your desk is the one you're supposed to use. Okay.
I got you.
All right. So my question is, this is the number one missed algebra thing ever. This very first thing she starts with, I love this. This is great. What is the difference between negative 6 to the 4th and the quantity of negative 6 to the 4th? Sasha?
When there is no the...
Parentheses?
Yeah.
Mm-hmm.
The sign is not under the...
It's not inside the parentheses. Yeah, it's not part. Very good. These parentheses tell us everything. This 4 is affecting everything in the parentheses. The parentheses are right underneath the 4, so that 4 is affecting everything in the parentheses. And if that 4 is affecting everything in the parentheses, it's saying repeat negative 6 4 times. So negative 6 times negative 6 times negative 6 times negative 6. So the answer will be a positive or a negative? A positive, okay? So what is it, 1296? Yeah. Okay. On this one, negative 6 to the 4th, what is the 4 affecting? Just the 6. It's not touching the negative. It's only touching the 6. So this one is saying, hey, it'd be a negative, and then it's saying repeat the 6 4 times. So this response is going to give you a negative answer. And it's really important. Now, we have calculators, but this is the number one algebra mistake all the time, okay? Pay attention, and this class is for that. Here we have, so this turns into negative 1296 times, what is negative 1/4 squared? What does it mean? Yeah, again, you can think about it. I love really thinking about the meaning of things. So it really means negative 1/4 times negative 1/4, which is going to give you? 1/16. Multiplying straight across. Positive 1, 4 times 4 is 16. Can we type all of this into our calculator? Yes, you can, okay? But again, it's important to know why. This becomes, if we were to multiply straight across, negative 1296 times 1 is negative 1296. 16 times 1 is 16. So 1296 divided by 16, I would get a negative 81. But again, this one had all numbers. Our calculators work really well if you use them correctly. But that is the key, if you use it correctly. So if you did type it in with your calculator, with all the parentheses and everything, it'll work just fine. How do you want to do number 2?
4.
Did you just type it in your calculator? You did just type it in? Oh, did you? How would you work out number 2?
Did you start?
5 to the 0 over, oh, so these don't have the same base. I was thinking I could do the quotient rule, but that won't work. Oh, we could flip it around. Okay, I see a negative exponent here. This is one thing we could do. So, 5 to the 0. This 3 to the negative 1 is unhappy where it is. So I could move him up. It becomes 3 to the now happy 1. Now, I am doing this. There are 70,000 different ways to do this, just in case you're curious, okay? But I heard someone say it's a negative exponent. Can we move it? So sure, we can. All right. What is 5 to the 0? 1. All right. So that is 1. And then we have 3 to the first is 3. And all of that is to the negative 2 power. Oh, do I need to write 1 times 3? No, I don't. Okay. So that becomes 3 to the negative 2 power. What is 3 to the negative 2 power? 1 over 9. 1 over 3 squared. Good. I'm sorry if you said that earlier. I did not. Oh. All right. So again, we have that negative exponent. So that wants to go into the denominator where it becomes happy, and then we can square it. Okay? There, again, exponents, I think the hardest part about exponents is that there are literally 37 different ways to do them. Okay? So many different ways. Okay. Here we have numbers, and we have letters that are the same. They have the same base. So what I'm going to do is I'm going to go ahead. Everything here, I think this is important to talk about. Everything here is connected by multiplication. So I could really stretch it out. And of course, you remember there's this lovely property called the commutative property that allows you to, turn things around. 5 times 4 is the same as 4 times 5, right? Yeah? So I can rearrange and do these numbers together, 3 times 8, and then p to the negative 2 times p to the 6. We can change the order. Again, this is a lot of steps, but these are notes. I always do my steps in notes so that there's no confusion on what I'm doing. You don't necessarily have to do all the steps in your work, okay? All right, negative 3 times 8. Negative 24. Now, these have the same base. The p stays the same. And what do we do to the exponents? Add the exponents. Negative 2 plus 6 is 4. So there is our lovely little answer. Could we have gone directly there? Yes. Absolutely. Pretty easy to go directly there. All right, number 4 here. Number 4, I have this lovely little quotient here, and I need to clean that up. Avery. Yeah, so what would you, if you want to, you see that you've got some negative exponents. I have y to the negative 2, I have y to the negative 3. Guys, shh. And you're saying, could we switch them both? Does other stuff move? No, just the thing with the negative. So we could do that. I'm not going to right now, because I'm going to use the rules this time. So I see a 57 and a 3. I can divide those numbers. How many times does 3 go into 57? Oh, does it go evenly? 19? Okay. 3 goes into 57 19 times. Now, I have x to the 4th, and x to what power? 1. Very good. There's a little invisible 1 there. Very important. What is x to the 4th over x to the 1? X to the 3rd. They have the same base, so we can subtract those the exponents. So we get the base of x. 4 minus 1 is 3. We can subtract those exponents. And then I can do the same thing with the y's here. They have the same base of y, and I can use the same property. We're going to do negative 2 minus a negative 3. Very good. We get positive 1, right? Negative 2 minus a negative 3 becomes positive 1. So that's good. And the rest of this problem is a subtract 11x cubed y. So we have 19 x cubed y minus 11 x cubed y. Can I combine those? Okay, because they are like terms, and that becomes what? 8x cubes y. Okay, so that's an interesting one. All right, let's look at number, what one do you want to do next? 5 looks harder to me. Let's look at 5. It doesn't look too bad, that's good. So I see this group here raised to a power of 2. I need to clean that up. We want to get rid of our grouping symbols, so it makes sense that I'd want to clean this part up first. So I'm just going to rewrite the 3/4 r to the negative 2 s to the 5th. And this whole group is being squared. What do you get when you square that whole group in parentheses? Perfect. Negative 4 squared is positive 16. R cubed to a power of 2. Multiply those powers. We get r to the 6th. And this is s to the 1st squared. So we get s squared. Multiply those powers. 1 times 2 is 2. Now that we've got rid of our grouping symbols, now we can combine anything. What's 3/4 of 16? 12. Very good. Then we have r to the negative 2 times r to the 6th. They have the same base. What do you do with the exponents? Add them, so we get r to the 4. Good. And then s to the 7th. Yes. S to the 5th times s squared is s to the 7th. Very good. All right. All right, number 7. Number 7. There's a lot of ways you can do this. What are you thinking?
You should start out like trying to divide 39 and
Reducing, yeah. It doesn't reduce, you're right. Darn. But certainly that was my first thought. Because when I think, should I square it, then it becomes super big. I don't want to deal with big numbers, right? But they don't really reduce, you're right. Do they? They do reduce. Yeah, they do reduce. They're both divisible by 3. So yeah, when I look at those numbers and I think about things that I can do, I want to simplify first. So I'm going to clean up inside as much as I can here. So we're going to work inside. They both divide by 3 here. 39 divided by 3 is 13, and 24 divided by 3 is 8. C to the 7th divided by c squared becomes what? C to the 5th on the top or bottom? It should be up top, yeah. Is that how I wrote it okay? It is okay, so I could have stuck to a fraction, 13 over 8. When you use the rules, it's important, we would do top minus bottom, right? That rule is defined, the answer goes in the numerator always, okay? Sometimes you would get a negative exponent, and then that would shift to the bottom, okay? But, so the rule is that it would go in the numerator. I'm okay writing it like this as well. It's another way to write it. D to the 4th divided by d to the 5th. D to the negative 1, yes. So it would be d to the negative 1 if I just apply the rule. Or I can think, if I think about expanding that, d to the 4th, d on top. D to the 5th, d on bottom. Where's the leftover d's? On the bottom, okay? That's why I really like expanding, because I would go just right there. d to the first is going to wind up in the denominator, okay? Here we have d to the negative 1. I'm going to have to move it to the denominator, okay? But before I do that, I'm just going to keep going here. This whole thing is still squared. And so I need to square every single thing. So what is 13 over 8 squared? 13 times 13? 169 over 8 times 8? 64. Then we have c to the 5th being squared becomes c to what power? C to the 10th. Multiply your powers. And then here I have d to the negative 1 squared. So we multiply those, we get a negative 2. Where does d to the negative 2 go? Downstairs. Got to move it down to make it happy. That is a great answer right there. And this one would still have to be squared. You'd still get the same thing. Again, lots of ways to do this. All right. How do you feel? Okay. Do you want to do another one or you want to call it? Good? You good? Okay. All right, excellent. So watch those rules. I'm going to give you a little practice here. Punchline.